Good morning, students. Welcome back with another class. We discussed yesterday about the IUPAC nomenclature of carboxylic acids and esters. Today's lecture is about the chemistry of acetic acid, which means what is acetic acid, how it is prepared, what are its physical chemical properties, and what are its common uses. So, as you all know, acetic acid, the IUPAC name, International Union for Pure and Applied Chemistry, IUPAC. The IUPAC name of acetic acid is ethanoic acid. Right? Ethanoic acid, commonly called acetic acid because it was first isolated from vinegar, and at the time when it was realized that most of vinegar is acetic acid, at that time the language of the world was Latin, and vinegar is called acetum in the Latin language. So acetic acid is used every kitchen, almost every kitchen, every house has the acetic acid, and we put it in the soup, and it also has many uses. First thing first, how can we prepare acetic acid? So the first and most common method, we go with preparation of acetic acid. So what is the first and most important method of making acetic acid? The natural method of making acetic acid is from wood. Yes, wood. If you know, I have taught you already, when wood from the trees undergoes destructive distillation, which means when it is strongly heated, what? Destructive distillation, right? Strongly heated, when wood is strongly heated, you get fire, but since fire is not a chemical substance, it's just the energy, you get three different products. One is the solid product, other is the liquid product, and then we have the gaseous product. Now, the solid is basically wood charcoal. If you know, wood charcoal. When the wood is burnt and then you have a silver color powder left, it mostly pure carbon. It is obtained from destructive distillation of wood. The gas is mostly natural gas, methane gas. It is released, and it becomes the part of the fire, and it is burnt in the process. This liquid is dark brown color, and if you have seen wood burning, then from the other's end, from one end, let's say this is a wood, here it's burning, okay, there's a fire is over here. From this side you will see small bubbles of the brown color liquid will be produced. This liquid is called pyroligneous acid. It's a very strong acid. It contains many liquids. At the top, it's methanol. So methanol is poison, so pyroligneous acid is also poison. The second is acetone. Right? It also contains acetic acid. and methyl acetate, which is an ester. Okay, methyl acetate is an ester. Also, many other organic compound liquids are present in the pyroligneous acid. Okay, so pyroligneous acid is a highly acidic liquid, and it contains different type of important organic liquids such as methanol, acetone, acetic acid, methyl acetate, etc. Now, how can we separate acetic acid from the pyroligneous acid? We use a technique called fractional distillation. Fractional distillation. Now, fractional distillation is a technique where different liquid in a mixture are heated. When they're heated, different liquids are boiled at different boiling points, and then the vapors are produced. If those vapors are separated and then condensed back to liquids, you can isolate all these. Okay, so this is basically separation, a technique for separation of liquids from a mixture. At different boiling points. Now, different liquids have different boiling points, so that's why they can be separated very easily. Suppose this is a flask. All right, excuse me for my drawing. Okay, this is a flask. It's called distillation flask. Distillation flask. This is a big flask, mostly contains the mixture of all the liquids. Okay, it has a cork so that the vapors cannot escape from here, but a thermometer is inserted across this so we can see the temperature, and this end is where the vapors will escape. But if the vapors escaped in a gaseous form, they will go out, so we have to cool the vapors so that they become liquid again. So here we connect a condenser. Now, a condenser is basically glass pipe, and which grips on this with the help of a cork, and then here there's a pipe which is going round and round. Connect to this one. I don't know how I make it. So the vapors of the liquid come here and they flow in this circle way. Okay, and then here is a input, water from tap. Now, tap water with the help of a rubber pipe comes in, gets inside this condenser, but these vapors are exclusively going through this pipe. So this water would only surround it and not mixed in it. All right. So then this will go connect here. Right. So this water coming from tap, and it will drop into the basin or sink. The purpose of this water will just to move around this one, the interior glass pipe, so that the cooling is provided to the vapors. And then from here we use another flask. It's called the distillate flask, distillation flask, and then you have a distillate flask. Basically, it contains the liquid which is separated. So just suppose you mix 4 liquids, all right, and then you start heating them, all right. You will see a raise in temperature in the thermometer here, and then you will see no bubbling, nothing here. But as soon as the bubbling starts, you will see the thermometer will be fixed. The mercury will not go further up anymore. Let's say it is fixed at 56 degrees Celsius. Now 56 degrees Celsius, bubbles are produced here, vapors are made, they are cooled down, and you can see drops falling into the distillate flask. Okay? They are dropping here. So the bubbles will be produced at this temperature, go through this interior pipe, okay? The water running from the tap coming in, surrounding this interior pipe, falling into the sink for a cooling effect, and the droplets of the liquid will drop here. As long as the bubbling is taking place and the dropping of liquid taking place, the temperature will not increase, because at that time all the energy provided, heat from here, will be converted into vaporizing the molecules. But remember, only the molecules whose boiling point is 56 degrees C. So remaining liquids will stay in the distillation flask. However, anywhere if there is the liquid of 56 degrees C, it's gonna transfer here. As soon as the bubbling stops, the dropping stops, you will see a rise in temperature. You can now separate this flask and mark that this is 56 degrees Celsius. All right. And then you will see an effect, a similar effect taking place at 72 degrees Celsius. So you can put another distillation flask and fill with it. All right. And then so on and so forth. You can also see at 65, 64 degrees C, 80 degrees C, 100 degrees C, different, you will see that different liquids are going to boil. Now, when the one liquid is finished boiling, you can simply separate that liquid into another container. So once it is done, all liquid is finished, you can check that which liquid have these boiling points, right? This is water, benzene, methanol, ethanol, acetone. So you have 5 flasks separated from within one flask. This technique is called as fractional distillation. So through fractional distillation, you can prepare acetic acid from distillation of wood, pyroligneous acid. All right, this is the method. The second method of preparing the acetic acid basically is from acetylene, and this is the most common, the cheapest, and the most common method. Is number 2 in our book, from ethine. Our textbook ranks it at number 2 because pyroligneous acid is the natural product. So, but nowadays organic compounds are not preferably obtained from natural products, but they obtained from synthetic material. Now this is acetylene, ethine gas. Now I will take you to a very cheap mineral found in the mountains, calcium carbide. I told you already, okay? Once in the preparation of acetylene, how you prepare, if you go purchase ethine gas, it's going to be expensive. So how about we use a rather cheaper method? So calcium carbide, Ca, right? This is calcium carbide. It's called carbate. If you know, I told you in the classes, okay, these lectures are exclusively for the students of Navigator, and this is the continuity of what we do in the classroom. Calcium carbate is commonly called carbate in the normal language around here. We use it for ripening fruits such as mangoes, bananas, etc. Calcium carbate dissolves with water. In the ripening case, moisture, okay, and forms HC triple bond CH, the acetylene or the ethine gas, also called the ethine. And of course, calcium hydroxide. I have also told you that when you go to a gas welding shop who use carbide for gas welding, they produce ethane gas, they use it for welding, and there's a lot of white liquid around the shop. This is basically the waste calcium hydroxide. Now you convert calcium carbide to acetylene first, okay? Then the acetylene, HC triple bond CH. Now this is for the gas welding. Now if you want to make acetic acid or alcohol or aldehyde, nowadays this is inorganic compound, so inorganic material are obtained in large quantities, and they're very, very cheap, and they're very easy to handle as compared to the organic substances. Now acetylene can add water, but in the presence of sulfuric acid and mercuric sulfate. Dilute sulfuric acid and mercuric sulfate. Otherwise, it's going to catch fire with water, all right? At a normal temperature, less than water's boiling point, okay, 75 or 95 degrees Celsius, H will add here and OH will add here. This reaction we have done before in the chemistry of the ethane. You get CH2, double bond CH, and then OH. If you remember, I told you that this is unstable. Acetylene forming vinyl alcohol, right? The vinyl alcohol is unstable because the double bond between two carbon atoms is not preferable in presence of oxygen. Oxygen is more electronegative. It will obviously attract these pi electrons towards itself, all right? And this vinyl alcohol, which is CH2 double bond CH and then OH, the pi electron will shift towards the oxygen. This will only happen if this hydrogen is gone and it comes on the carbon here. So you get CH3, C double bond O and H. Now from vinyl alcohol, you get acetaldehyde. Acetaldehyde is also called ethanol. The calcium carbide breaks into acetylene. Acetylene forms vinyl alcohol. Vinyl alcohol rearranges to acetaldehyde. This is also a method of acetaldehyde. There's a rearrangement here. Why the rearrangement happens? Because the oxygen, being more electronegative, will attract the pi electrons from carbon and make a pi bond between, there will be a pi bond between carbon and oxygen. So there will be, hydrogen will move back to that carbon. This is acetaldehyde. Now acetaldehyde can be oxidized into carboxylic acid, acetic acid. You all know this. CH3, C double bond O. If you oxidize it, you make acetic acid. If you hydrogenate, reduce it, you make ethanol. All right. So the oxygen comes from the most famous oxidizing couple, the K2Cr2O7 and concentrated H2SO4. It becomes CH3, C double bond O and then OH. So acetaldehyde, ethanol becomes acetic acid. All right, it's called ethanoic acid. This is the cheapest way of making acetic acid rather than pyroligneous acid method, which is way more difficult than this. This is also used to make ethyl alcohol. If you reduce it here with hydrogen, it will make the ethyl alcohol. So this number 2 method is my favorite, everybody's favorite in the industry. This is the only method with which we can make acetaldehyde, we can make ethyl alcohol, we can make acetic acid and whatnot. Okay. Next is from alcohol. Now this method is, I don't think, well, I told you already, alcohols are oxidized to aldehydes, and aldehyde are oxidized to carboxylic acid. So if you have alcohol, let's say CH3, COH, there are 2 hydrogen here, one is H here, H here. If we oxidize it, we provide oxygen with the help of K2Cr2O7 and concentrated sulfuric acid. This hydrogen here will feel attracted to this oxygen, this one too. So when they both hydrogen are gone, there will be a pi bond between carbon and oxygen, and you will have CH3, C double bond O, and then H plus H2O. That's how you can convert ethanol into ethanol. Right? Methanol into methanol, ethanol into ethanol, ethyl alcohol into acetaldehyde. Now, this acetaldehyde or ethanol can be oxidized further, like here. Okay. H can be oxidized further, and it can form K2Cr2O7 concentrated sulfuric acid. This is same reaction. You get CH3, C double bond O, OH. So ethanol into ethanol and ethanol acetaldehyde into ethanoic acid. This is the third method, but basically it's the same. So this is how you can prepare acetic acid. Kindly do write it and also learn it. Okay, this is it. We go towards the properties, physical and chemical properties. Chemical properties mainly involve reactions. There are only few. So we begin with the physical properties. Okay, physical properties. Now, acetic acid is liquid. We all have seen acetic acid in our kitchen. We use it in our soups, especially in winter. It gives the soup that salty taste, sour taste. As an acid, it tastes sour. It is colorless liquid with a sour taste. Like when you put too much acetic vinegar into your soup, then you know it tastes pretty sour. So that's sour, okay? If you know. All right? It's also volatile, moderately volatile. Escapes out as in low boiling point, so it's like volatile. All right? And it is miscible with water. I told you. Miscible is soluble, but soluble is for ionic compound, miscible for the organic compound with water, alcohol, ether, etc. Easily dissolve in them. All right. So when we remove water from it, once we make a anhydrous acetic acid. If concentrated acetic acid is allowed to evaporate at some time, like it's a lot of acetic acid will give a little bit amount of solid acetic acid, it's called anhydrous acetic acid. And how we get it, let's say we have CH3, C double bond O, and then OH. This is acetic acid. Then we have HO, C double bond O, CH. They both are acetic acid. Okay. Now, if the water is removed, let's say this is water. Okay. Now, what's going to happen? What will be the product of this? It's going to be CH3, C double bond O, O, and then C double bond O, and then CH3. Anhydrous acetic acid, solid acetic acid. And this can also be shown as CH3, CO, CH3, CO bonded through O. That's how it's very hygroscopic. If you put it into water, like suppose you have a dish with a little bit water in it, okay? And then you put the solid acetic acid into that water, water will disappear. It will absorb the water, forming acetic acid. Okay, so it's like it has a ability to absorb water. Okay, these are the physical properties of acetic acid. Now we jump towards the chemical properties. Chemical properties of acetic acid. Chemically, of course, it's an acid. Not a very strong acid as HCl or the HCl or HNO3 or H2SO4. These are mineral acids, inorganic acids. They are called mineral acids. The Ka value, dissociation, dissociation constant. KSP, Ka, Kb. Ka is dissociation constant for acids. Of the mineral acid is about 10 power 8. It's very, very strong. Okay. When we compare it to our acetic acid's Ka value of acetic acid, then you will be surprised it is 1.7 10 power minus 5. Now you can see, you might be asking that if acetic acid is an acid, then how we put it into soup and drink it? Because its Ka value is very, very small. Okay, due to a small Ka value, it is not like the mineral acids, 10 power 8, 10 power minus 5, much difference. But in the organic chemistry, it is considered as a good acid because it is better than the acids in the organic chemistry. Let's say carbonic acid is also an acid. Carbonic acid, H2CO3, its Ka value is 4.3 10 power minus 7. So this between the weakest of acids and between the strongest of acids. So it's acid. Being an acid, what it can do? It can react with base and neutralize it. Yes. The OH and the H will form water and you will have CH3COONA, sodium acetate. This is acid. Acid, base, salt, water. Acid, acetic acid, base, sodium hydroxide, salt, sodium acetate. So if you use formic acid, you get sodium formate. If you use propanoic acid, you get sodium propanoate, the esters, sodium with sodium. So this proves that it's an acid. The second reaction which proves it's an acid is it can make salt with other basic oxide like lead oxide. You can say 2CH3 COOH with the lead oxide. It is basic in nature. Okay, it will form lead acetate, which is also a pigment, if you guys know, and water. So this is lead acetate. Lead acetate is also a pigment, and these two reactions prove that acetic acid is a moderate acid. Okay, so the first property is as an acid. Acetic acid as an acid. It behaves as an acid because of its action on alkalis. Second property of acetic acid, which I want to share with you here today, is esterification. This is our lecture in class 11 already going on. This reaction is important. You also have learned it when you were in first year, how carboxylic acids become esters with alcohols. Okay, alcohol, carboxylic acids, they form ester and water. So that's a simple one. Okay, there we go. This is acetic acid, CH3 COOH, and alcohol, C2H5OH. Whose acid? Acetic acid. Whose base? Alcohol. So alcohols OH and H2O. What are we left with? We have CH3 COO, then we have C2H5 plus H2O. So this is acetic acid. This is ethyl alcohol. This is ethyl acetate. From the naming of esters, you know, ethyl acetate. So this is by family an ester group. You will learn in future, tomorrow's lecture, that we mainly make our esters, different esters, from carboxylic acids and alcohols. Here, carboxylic acids, they lose hydrogen or proton, and alcohols lose the hydroxy group. So alcohol is going to react as a base. So this reaction basically is a reversible reaction, okay, and right. So this is you can make more acetic acid if you more ester if you have more hydrogen ion concentration on this side. So if you will read in the book, they will tell you that you have to put 1 to 2 drops of sulfuric acid. Now you might be wondering, what is sulfuric acid doing here? This is the Le-Chatelier's principle. Adding sulfuric acid will increase the H plus ion concentration on the reactant side. This will push the reaction towards the product side. So I hope you get it. If I have taught you Le-Chatelier's principle in first year, then it should be easy game for you. Third chemical reaction of acetic acid is its reaction with some chlorides and formation of the acetyl or acid halides, organic acid halides. Formation of acid halides. There are different acid halides, you know, HCl, HBr, HF, important inorganic acid halides. But similar acid halides can be prepared with the acetic acid. All right, That's why it's chemically important, because these acid halides then can make a variety of compounds. Okay, so how can we prepare acid halides from acetic acid? So we need acetic acid. Done. If it reacts with the SOCl2, thionyl chloride, this is acetic acid reacting with thionyl chloride. Okay, so the OH group of the acetic acid will be displaced by the chloride. Chloride will, the nucleophilic substitution reactions will take place, SN reactions, and you are going to get CH3, C double bond O, and Cl. This is acetyl chloride. This is the organic acid halide, acetyl chloride. Plus the sulfur will burn as SO2 will produce, and also hydrochloric acid. Now this acetyl chloride is the compound which is used to make new compounds. Now you need a thionyl chloride, SOCl2. The similar product can be achieved with PCl3 as well. CH3, C double bond O, OH, acetic acid, PCl3, phosphorus trichloride. In that case, you get CH3, C double bond O, Cl, right? Plus phosphorus, because OH and P, they will make POH3 or H3PO3. Now there are 3 chloros, so there will be 3 here and then 3 here as well. The same product can come with the SOCl2 or with the PCl3. All right. If you want acetyl chloride, you need the chlorides. If you want acetyl bromide, you need the bromides. These are important organic reactions, and we have seen them in the past papers of NTS. In this case, you get CH3, C double bond O, and Br. Just where the chloro is, there will be a bromo. And you have other product like POBr3, NHBr. Now this is acetyl chloride. This is acetyl chloride. This one is acetyl bromide. Now these acetyl bromides and chlorides make important chain. Lots of compounds are obtained from them because they are reactive in nature. Suppose if they react with ammonia, okay, if acetyl chloride, CH3, C double bond O, Cl, with ammonia, HNH2, this will make HCl, obviously, and you will have CH3, C double bond O, and NH2, the acid amide. This is used in laboratory a lot. We have used in the laboratory organic labs, and also to make fertilizers, the acid amides, acid amide. This one is acetamide because of the acetic acid, acetamide. The family is called acetamides. This is the compound name, acetamide. Okay, they can be propionamide, butanamide, butanamide, pentanamide, depending upon the carbons over here. So in the exam, if they ask us, how can you convert acetic acid to acetamide? You first use the SOCl2 to make acetyl chloride, and then the acetyl chloride will react with ammonia to make acetamide. This I have seen in the examination, convert acetic acid to acetamide, and then the students are saying there's no reactions, but there is one, so you should keep in mind this one. All right. The acetyl chloride, as I told you, is reactive. Acetamide is an important organic compound. If it reacts with the sodium acetate, it can form another important compound called acetic anhydride. All right. which is called the glacial acetic acid. In this case, you can increase the acetic acid very easily. So number 3, when it reacts with sodium acetate. Okay, so this is acetyl chloride, CH3, C double bond O and Cl. When they react with sodium acetate, it is C double bond O, then Na, but I will shift the Na on this side so you can understand. ONA. So Na plus O minus Cl minus NaCl. So you get what? CH3, C double bond O, and then bond to this carbon bond to this O, and then you have C double bond O. It was shown in the properties. It's called anhydric acetic acid or glacial acetic acid. The anhydric acetic acid, is called glacial because it looks like glass, crystals of glass. Anhydric acetic, of course NaCl. Now this is also an important thing we obtain from it. Number 3, it can react with sodium ethoxide to give you esters. Okay, so if you use sodium ethoxide, it's a kind of acid reaction that it does. There's a variety of compounds, just like the acid reactions in the alkyl halides. Now, alkyl halides are reactive, but acid halides, the acetyl chloride, is even more reactive than that ones. Okay, variety of compounds are produced from it. So if you take CH3, C double bond O and Cl, the acetyl chloride, right? And you use sodium ethoxide. It could be this way as well. Again, plus and minus NaCl. You have CH3, C double bond O, and then OC2H5. This is ethyl acetate. These are also organic compounds, the ester family. So the acetic acid can form acetyl chloride with thionyl chloride, or with the phosphorus trichloride, and then that acetyl chloride can make with ammonia acetamide. With sodium acetate, it can form acetic anhydride, and with sodium ethoxide, it can form you the esters. All right. Last reaction of the carboxylic acid is decarboxylation, removal of the carboxylic group. Okay, it's called decarboxylation, removal of carboxylic group. This was the first organic reaction I taught you, preparation of methane gas, if you remember. Okay, all right. So when we take sodium acetate, CH3, COONA, and put into NaOH, basically I need a time here. The NaOH is called caustic soda, but it alone will not cause the decarboxylation. Calcium oxide is called quicklime. When they are mixed, the mixture of sodium hydroxide and calcium oxide is called soda lime. The soda, the lime. Okay, when it react with that, it forms Na2CO3. Na2COO. Okay, so when Na2CO3 is formed. Sorry, I missed the oxygen. NO2CO3 is formed. You have the methyl group and the hydrogen only. So it's going to make form what? It's going to form CH4, which is methane. It was the first meth reaction also. So this is methane from sodium acetate. In this reaction, the carboxylic group is broken, so it's called decarboxylation. This is the these were the chemical properties of the acetic acid. Uses, there are many uses of acetic acid. There are countless uses. Most important use is in our kitchen. It is used as a vinegar directly. It requires some purification, some removal of some other species, some distillation. It's called naturing. Once you nature it, you can prepare it for direct human use as a vinegar. All right. It is used to make compounds like acetamide, okay, acetylation. If you know benzene, Friedel-Crafts acetylation. So the compound are used there, and it can make many other compounds such as leather, and it is also solvent, also used in the factories and also in the laboratories. I will recommend you to check your textbook and check the uses from there. If there's any confusion, you can ask me. So student, with this, our lecture ends. The chemistry of acetic acid is a pretty long one. I hope you are not bored. All right. Good luck and show me your work as soon as you are done with it. Thank you. Goodbye.